Welcome back. Let's learn about some basic 3D formulas. Alright, so previously you were introduced to the three-dimensional coordinate system, and you saw how we can plot points within that 3D coordinate system. But now what we want to do is look at some formulas that we can use for points within the 3D coordinate system. In particular, we're going to be looking at three different formulas, and each of these formulas should be familiar. They're just going to be an extension of some formulas you've used before in the two-dimensional coordinate system. All right, and so those three formulas are the distance formula. That's the formula that lets us calculate the distance between 2 points in a coordinate system. Then next up we have the midpoint formula. That's the formula that allows us to find the coordinates of the midpoint between 2 points. So in other words, if we're looking at these 2 points right here, P1 and P2, we want to find the point directly in between those 2 points. We could find that point and its coordinates using the midpoint formula. And then finally, the last formula that we will look at is related to circles, except we're not going to be working with circles anymore in the three-dimensional coordinate system. We're going to be working with a different shape. In fact, it's not really a shape, it will be a solid. And I'm not going to tell you what it is right now. I'm not going to spoil it, but you will get to see what that solid is when we get to this formula in the video. Okay, so that's what we're going to be doing in this video. We're going to look at how we can extend the distance formula, the midpoint formula, and the formula for a circle into the third dimension. And so let's get started with our first formula. All right, so the first formula we're going to look at is the distance formula. Remember that in the 2D coordinate system that we can calculate the distance between any 2 points by using this formula, right? If we have 2 points, P1 and P2, where P1 is at the coordinates x1, y1, and P2 is at the coordinates x2, y2, then the distance between point 1 and point 2 is equal to the square root of the difference in the x value squared plus the difference in the y value squared. Okay, and so if we want to extend this formula into 3 dimensions, what do we have to do? Well, if we have 2 points, P1 and P2, that both have an x, y, and z coordinate, we can use the same formula that we use in 2 dimensions, but just extend it for that third dimension. Because now we don't just have an x and y coordinate for our 2 points, we also have a z coordinate. And so we can extend our formula by just simply adding on another part underneath that square root, right? We can add the difference in our z coordinates squared. So we'll have z2 minus z1, and then we'll square that quantity and keep it under the square root. And this is the distance formula in the three-dimensional coordinate system. Okay, so it really is just that simple. You just tack on another part underneath that square root that accounts for the difference in the z values for your coordinates. And so let's take a look at a quick example of using this formula. Here we want to find the distance between the points 1, -2, 4, and 6, -2, -2. And here's our distance formula here. And so if we want to calculate the distance between those 2 points, let's use that distance formula. The distance will be equal to the square root of the difference in the x coordinates squared. And our x coordinates are 6 and 1. So we'll have 6 minus 1 squared. Then we'll add that to the difference in the y coordinates squared. And the y coordinates are both -2. So we're going to have -2 minus -2. And that quantity is squared. And then we're adding that to the difference in the z coordinates squared. And the z coordinates are -2 and 4. So we'll have -2 minus 4. All right, so we're taking the square root of the difference of the x coordinate squared plus the difference in the y coordinate squared, and then we're adding the difference in the z coordinates squared. Okay, so all we have to do now is simplify. 6 minus 1 is 5, so the distance is equal to the square root of 5 squared plus -2 minus -2 is the same as -2 plus 2, right? Those negatives cancel out and become positive, and -2 plus 2 is 0. So we have 0 squared, and then we're adding -2 minus 4 squared, and -2 minus 4 is -6. So we have -6 squared. All right, now 5 squared is 25, 0 squared is 0, and -6 squared is 36. So this is equal to the square root of 25 plus 0 plus 36, and 25 plus 36 is 61. And so the distance is equal to the square root of 61. And that can't be simplified any further. This is in its simplest form. And so that is the distance between these 2 points in the 3D coordinate system. The distance between this point and this point is the square root of 61. Okay, so that's the distance formula in 3 dimensions. It's basically the same as using the distance formula in 2D, except now you just also need to account for those z-coordinates. All right, let's take a look at another formula. Next up, we have the midpoint formula, which we used in the 2-dimensional coordinate system to find the midpoint, or the point between 2 points. So if we have a point P1 and a point P2 with coordinates x1, y1, and x2, y2, we could find the midpoint for those 2 points by taking the average of their coordinates. All right, we take x1 plus x2, divide by 2, and that's the x coordinate of the midpoint. And then for the y coordinate of the midpoint, we take y1 plus y2 and divide by 2. It's just the average of the coordinates from those 2 points. So if we want to extend this into a third dimension, we just have to take into account that third coordinate of the z-coordinate. And so that will look like this. For 2 points, P1 and P2, where P1 has coordinates x1, y1, z1, and P2 has coordinates x2, y2, z2, the midpoint will have 3 coordinates, an x-coordinate, a y-coordinate, and a z-coordinate, where the x-coordinate is the average of x1 and x2, the y-coordinate is the average of y1 and y2, and the z-coordinate will be the average of z1 and z2. So that will look like this. We'll have z1 plus z2, and that will be divided by 2. That represents the average of those 2 coordinates. And so this right here is the midpoint formula. We can find the point between 2 points in the 3D coordinate system by simply taking the average of the x, y, and z coordinates for those 2 points. Let's take a look at a quick example. All right, so here's our example. We want to find the coordinates of the midpoint of the line segment joining 3, 4, 6 to 1, 8, 0. All right, and so to do that, we just need to use our midpoint formula and take the average between the x coordinates, the y coordinates, and the z coordinates. And so let's do that. Let's find the midpoint. What we will do is take the average of our x coordinates. So we'll have 3 plus 1 divided by 2, right? We add them together and then divide by 2. Then we'll take the average of the y coordinates. So we'll add 4 and 8 and divide by 2. So we'll have 4 plus 8 and divide by 2. And then we'll take the average of the z coordinates, which are 6 and 0. So we'll have 6 plus 0 divided by 2. And that's going to be our midpoint. We just have to simplify it. And so 3 plus 1 is 4, divided by 2 is 2. So we'll have 2 comma 4 plus 8, which is 12, divided by 2 is 6. So our y coordinate is 6. And then for the z coordinate, we have 6 plus 0, which is 6, divided by 2, which is 3. So we have 3 as our z coordinate. Okay? And so 2, 6, 3 is the midpoint, or the point in between these 2 points. Or you can view it as the midpoint of the line segment connecting these 2 points in the 3D coordinate system. Okay, so just like the distance formula, it's really not anything new. We're just extending it to a third dimension. We just now work with z coordinates in addition to x and y coordinates. Okay, let's take a look at the final formula that we're going to extend into the third dimension. All right, so the last thing that we're going to do in this lesson is extend the idea of circles into the third dimension. All right, so just as a refresher, the standard equation for circles in the 2D coordinate system looks like this. We have x minus the x coordinate of the center of the circle, and that's squared, plus y minus the y coordinate of the center of the circle, and that's squared, and it's equal to the radius squared. All right, so here's our circle graphed in the 2-dimensional coordinate system. The radius is the distance from the center to the outside of the circle. That's the value that's being squared in this equation. And then the center of the circle is represented by the point h comma k. All right, so whatever h is, that's the x coordinate of the center, and whatever k is, that's the y coordinate of the center of the circle. All right, and so now if we extend this equation into the third dimension, what's going to happen? Are we still going to have a circle, or are we going to have something else entirely? Well, if you think about your 2D shapes and your 3-dimensional solids, what do you typically associate with a circle? Hopefully you're thinking about a sphere, and that is exactly right. When we extend this equation, this standard equation of a circle, into the third dimension, we are now going to have the standard equation of a sphere. And so here's what that's going to look like. The standard equation for a sphere looks very similar to the standard equation of a circle, except now we have an additional part that accounts for the z-coordinate of the center of the sphere. Right? If you look at this graph here, we have a sphere. I did my best to try to show you that this is a sphere and not just a circle. It is hard to draw three-dimensional objects in a 2D format. But here's our sphere, and it has a center point with the coordinates h, k, l. All right, and those coordinates are used in this equation. We have x minus h, the x-coordinate of the center, and that's squared, plus y minus k, the y-coordinate of the center, and that's squared, and then we have plus z minus l, the z-coordinate of the center, and that's squared. And then it's still equal to the radius squared. Just like a circle, a sphere has a radius, which is the measurement from the center of the sphere to any other point around the sphere. Okay, so really the only difference between the standard equation for a circle in 2D and the standard equation for a sphere in 3D is just this extra part that accounts for the z-coordinate of the center of the sphere. And so really this standard equation, the standard equation of a sphere, is your first introduction to actually graphing surfaces such as a sphere in a 3D coordinate system. We don't really get to graph any more surfaces till later in Calculus 3, and so this is a little bit of a preview into some of the things you get to do later on. All right, but before we close out this lesson, let's look at a couple examples where we get to work with this standard equation for a sphere. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, so here's our first example. We want to find the standard equation of the sphere with a center of 0, 2, 5 and a radius of 3. All right, now if you know the form of the standard equation for a sphere, this is a very easy problem. Right? We're given the center, we're given the radius. Those are the two things that we need to set up this standard equation of a sphere. We'll have x minus the x-coordinate, and that will be squared. Then we'll have plus y minus the y-coordinate, and that will be squared. And then we'll add that to z minus the z-coordinate, and that will be squared. And we'll set that equal to the radius squared. So let's do that. Our equation of this sphere will look like this. We'll have x minus the x-coordinate, which is 0. So we have 0. And then we'll square that, and we'll add that to y minus the y-coordinate, which is 2. So we'll have 2, and we'll square that, and we'll add that to z minus the z-coordinate, which is 5. So we'll have 5, and we'll square that, and that will be equal to the radius squared, which is 3. So we have 3 squared. Okay, now I guess you could leave it in this form. That's perfectly fine, but there's a couple things that we can simplify here. X minus 0 is just x. So this is x squared plus y minus 2 squared plus z minus 5 squared, and then we can set that equal to 9 since 3 squared is 9. Okay, but that's all there is to this problem. That is the standard equation of the sphere with a center of this point and a radius of 3. All right, let's look at one more example for this video, which is slightly different than this example. Okay, so for this last example, we want to complete the square to write the equation of the sphere in standard form. And then we want to identify the center and radius of the sphere. All right, so if you've worked with circles in the past, this type of problem should be familiar. One of the things that you learn how to do with circles is how to take the equation of a circle and complete the square for x and y in order to rewrite the equation into standard form. All right, and so all we're doing here is extending that into the third dimension by now working with z as well, and the equation no longer represents a circle, it represents a sphere. All right, so the first thing that we should do here in order to work on completing the square, in order to get this equation in this form, is we should group together our terms using the same variable. What I mean by that is we should group together our x terms, our y terms, and our z terms. All right, so if we do that, we'll have x squared, and then I see negative 2x, so I'll write minus 2x. And that's all the x terms, but now let's look at our y terms. We have y squared and 6y. So we'll have plus y squared and plus 6y. And then let's add our z terms, which are z squared and 8z. So we'll have plus z squared and plus 8z. And then we have this leftover plus 1. I'm just going to subtract that over to the other side of the equation. So this will be equal to negative 1. Okay, so now we have our x terms, y terms, and z terms. And what we want to do for each of these sets of terms is complete the square so that we can write them in this format, where we have x minus some value squared, y minus some value squared, and z minus some value squared. All right, and we're set up pretty nicely here. We have an x squared term, and then a term where we have x to the first power. We have y squared, and then a term where you have y to the first power, and then we have z squared, and a term where we have z to the first power. So this shouldn't be too bad. All we have to do to complete the square for each of these sets of terms, for x, y, and z, is take the coefficient of the term where the variable is to the first power, divide it by 2, and then square it. Whatever that value is, we then want to add to both sides of the equation. And I should mention this real quick. In order to complete the square the way that we're going to do it here, it's important for the coefficients of the squared terms to be 1, which in this case they are. Right? We just have x squared, y squared, and z squared. We don't have 3x squared or 4y squared or 7z squared. The coefficients of our squared terms are just 1, and so we're good here. Okay? So let's work on the first one here. We're going to take this coefficient of negative 2. It's the coefficient of x to the first power. We're going to divide that by 2. Negative 2 divided by 2 is negative 1. And then square that. Negative 1 squared is positive 1. So we're going to add positive 1 to both sides of the equation. So we'll add that over there as well. Okay? Now for the y terms, we have 6y. That is the term where y is to the first power. We'll take 6, divide by 2. That's 3. And then square it. 3 squared is 9. So we're going to add 9 to both sides of the equation. So we'll have plus 9 and plus 9. And then we'll do the same thing for z. We have 8z. Z is to the first power, so we use this coefficient. We take 8, divide by 2. That's 4. And then square it. 4 squared is 16. So in here, we're going to add 16. And we also need to add 16 to the other side of the equation. All right, and so now we can complete the square for the x terms, the y terms, and the z terms. All right, so all we have to do to rewrite these three quadratics into this form is to remember what that value was that resulted when we divided that middle term by 2. All right, so for this first one, we divided negative 2 by 2 and got negative 1. So to rewrite our x terms in this form, we will have x minus 1 squared. All right, and then we'll add that to our y terms, but written in this form. Remember that we divided 6 by 2 and got 3. So to rewrite that, we'll have y plus 3 squared. And then for z, remember we divided 8 by 2 and got 4. So to rewrite that, we'll have z plus 4 squared. All right, and that's going to be equal to these numbers added together. Negative 1 and 1 cancel each other out, so we can cross those out. And then 9 plus 16 is 25. So this is equal to 25. And that right there, we can box that in. That is our equation of the sphere in standard form. We have x minus some value squared plus y minus some value squared, although it is y plus 3. Technically, it's y minus negative 3. We'll get to that in a second. And then we have plus z minus some value squared as well. Once again, that would be minus negative 4. And then those three terms are equal to 25, which is equal to some value squared. And so now we're going to take a closer look at that because we want to look at this equation of a sphere in standard form, and identify the center and radius. So using what we know about the equation of a sphere in standard form, we can identify the center and the radius. Remember that the center is HKL, where H is that value being subtracted from X, K is that value being subtracted from Y, and L is that value being subtracted from Z. So H is pretty easy. H is 1. So the center is 1 comma the value being subtracted from Y. But if we have Y plus 3, then it would have to be Y minus negative 3, like I said. Remember that if you have y minus negative 3, those negatives would cancel out, and so that would be y plus 3, all right? So k is going to be negative 3, so we have negative 3, and then for the z-coordinate, we'll have negative 4 for the same reason that k was negative 3, right? We have z plus 4, and so that would be the same as z minus negative 4, so negative 4 is the z-coordinate of the center of the sphere. All right, so that's our center, and then r, the radius, will be the square root of this value right here, and the square root of 25 is 5, so the radius r is equal to 5. All right, so that's the center of our sphere, and that's the radius of our sphere. We could find both of those values from this standard equation of the sphere. All right, and so with that, that is it for this lesson. But if you do want to see some more example problems, feel free to check out my examples video that's linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.